Hello everyone. In today's lesson, I want to take you on a bit of a thought experiment. I want us to go back in time 2,000, 3,000 years ago and put ourselves in the place of an early human with early civilization. And I want us to try to figure out, why is it that mathematics even came to be? Why is it that people spent their time for the next 2 and 3,000 years working on the fundamental building blocks of modern day society? And the answer that I come to is that if you imagine in a time when entertainment was dissimilar from what we have today, and you're looking across and you're seeing fields and hills that all seem to roll in a similar nature to each other, and you look at the waves and how the waves crash, and even more so than that, you look up at the stars. And if you've ever seen the stars on a beautifully clear day, you know what I'm talking about. It's just a stunning sight. There's a reason why poets refer to it as the heavens. It's gorgeous. And to think that there may be a method to the movement across the sky, that there might be a pattern that man could understand, was a really inspiring idea. Were these just controlled by the gods or by unworldly forces, or was there perhaps a way that man could put themselves in the same role as God and really understand and sometimes even take advantage of these patterns in a predictable and necessary way? And so today, I'm going to use that same idea of saying, can we recognize these patterns, and can we use shapes and visuals around us to really anchor down these difficult ideas to cover one of the fundamental concepts of algebra, which is factoring. And many of you have probably heard of factoring. Factoring talks about trying to pull out or look for common factors from two different entities. And I'm going to show you that all these things that you may have been exposed to in earlier high school math classes are in fact things that you could represent just by playing around with some pieces of tile or some paper cutouts on your table. And I'm going to show you how to do that in just a second. So let's start with doing just a quick review if we can. So I want us to do a quick talk about, is it true that we have 5 times parentheses 1 plus 2 equals 15. We've been taught this is true. We could even work with some of the algebra rules that we know to prove that this is true. We could use, for example, the rule of parentheses to say that parentheses come first in our order of operations, to say that I could rewrite this as 5 times 3 and that would be 15. We could also use our distributive property and say that we could affect the 5 to the 1, and then also take that 5 and multiply it into the 2, and that would get us 5 times 1 plus 5 times 2, and that together that would be 5 and 10, getting us the 15. But I want to show you one other reason. Why is this true? Where does this come from? It's because of pictures. Imagine that I had read this instead using words, and I said that I had 5 groups of 1 and 2. Well, first we might try to describe what the 1 and 2 is. And if we were trying to explain this to a young child or somebody who is not familiar with math, we'd say, well, if I have 1 and 2, it's 3, because if I take one object and I combine it with 2 more objects, that I have 3. And we could think of this as the meaning of addition, us trying to grow this quantity by adding in more things. And we could think of 5 groups of this 1 and 2 as being just that. We could have 5 groups of this 1 and 2. That's 2 groups. We could have 3 groups. We could have 4 groups. And we could have 5 groups. And if I have 5 groups of 1 and 2, notice what we have. We have 5 groups of 1, in other words, 5 units, and we have 5 groups of 2, which is our 10 units. That's where these numbers 5 and 10 come from. It's the justification that allows us to distribute, is because that's the meaning. We can look at that as 5 groups of 3 if we wanted to look at it going sideways, or we could look at it as 5 groups of 2 and 5 groups of 1 going top to bottom. Kind of interesting. So here's the question. Is it true, let's take a look at this next one here, that I could do all of the work that I have shown? I have 3 plus 4 times the quantity 2 plus 5. And if we take a moment and we just try to follow the pattern here, a useful skill when you're working in mathematics is just to take a moment and step back and say, can we determine what the person was thinking? Then here we can see that the 3 plus 4 appears 2 times in the next line, and that we have the 2 and the 5 each being multiplied by it. And so we can recognize that what we're doing here is, again, distribution. It's the same idea as we had up here. We have 3 plus 4 groups of 2 and 3 plus 4 groups of 5. Well, then that's going to be 3 plus 4 groups of 2 and 3 plus 4 groups of 5. That's exactly how we're able to rewrite this with the same meaning, just with a slightly different appearance. Well, then the same idea applies here. Now I have 3 plus 4, and I have 2 of them. Well, that would be 2 3s and 2 4s. That's where I get the 2 3s and the 2 4s. Similarly, for the next one, I have 3 and 4, and I'm multiplying that by 5. So I'm trying to create 5 of the 3s and 5 of the 4s. That's why I'm able to distribute going backwards. Algebraically, you're probably used to seeing us make some notation like this to show that the 2 affects the 3 and it affects the 4 using multiplication. And similarly, the 5 affects the 3 and a 5 affects the 4. And this is how we learn that distribution works, whether you're multiplying in the front or whether you're multiplying in the back. Which is why we say that in multiplication, it doesn't matter whether or not you have the first thing times the second or the second thing times the first, this commutative property, we can actually flip it around. Or we could just recognize that going backwards really is no different than going forwards with multiplication. All of this to say that in order to get to very simple answers, we can start with very difficult places and then build from there. And I want to show you one other one that I just thought of. Imagine that I was trying to multiply two difficult numbers. Maybe I was trying to do 24 times 15. There's no reason I couldn't look at this as 20 and 4 times 10 and 5. And in fact, using this distribution, it might make my math a little bit easier to do on my head or on my scratch paper. So I have 20 and 4 times 10 gets me 20 and 4 of those 10s. I'm just doing the same distribution I did above. And then I have 20 and 4 times 5. That'd be 20 and 4 times 5. And I could multiply that on through. So 20 and 10 gets me 200. The 4 and the 10 gets me 40. The 20 and the 5 is going to get me 100. And then the 4 and the 5 gets me 20. So all in all, it's going to get me 360. Now this might seem a little bit strange to you because you're probably used to two-digit multiplication being like this, where we take 24 and we multiply by 15, and then we say 5 times 4 gets me 20, and I put it up here, and then I got the 5 times the 2 gets me 10, but then I add 2 to it, so it gets me 120, but then I have on the next line down, I put a 0 here for some reason, and then 1 times 4 gets me 4, and then I have 1 times 2 gets me 2, so I could add all that together, and I can get 360. Well, why is it that I have to move things around or get them just the same way that I had here? And the reason is because of this. My 120 is these numbers. It's my 100 and my 20, the things that happened from me trying to multiply 5 by both of the lines above. And why is it that I have 240? Well, because my 240 occurs from me trying to multiply the 10 times the 20 and the 40. That's exactly how we got this line. So it's the same idea. It's just that here we were taught some strange, weird little algorithm that makes no sense and that works simply because we were told it was supposed to. And here it makes sense because we understand why. And I'll show you how, even more than being able to understand why, we could actually represent this as a picture. But we'll come back to that in a little bit. That's a surprise for later. So for right now, let's just take a moment. And I want us to step back and I want us to play a game. Let's imagine that I wanted to represent all of the variables that we're used to in terms of pictures. So let's take a look. I have x squared, which is going to be this open box. I have a negative x squared, that's going to be a shaded box. I have an x, that's going to be a rectangle that is as long as x. And then I have negative x, that'll be a shaded rectangle that's as long as my box. And then I have 1, which is just going to be a little unit cube, and I'll have a negative 1, which is a shaded unit cube. So what I have here are all of my positives are just going to be these open boxes. My negatives will be these shaded in boxes. And we can see that, in fact, what we're really referring to here is the size, that these are x squared size because they're going to be an x by an x. And here I have a shape that is x big because it's going to be x length and 1 width. And here I have something that is 1 big because it's going to be 1 width and 1 height. So all of these are really just our areas. So the amount that's shaded here, the amount that's open is going to be our amounts. And we're going to see what happens when we try to represent things with pictures. Okay. Well, that's one nice way of thinking about it, but how do these interact? Maybe I want to know what happens if I take an x squared and I combine it with a negative x squared. Now, algebraically, we know what happens here. We know they cancel out. But again, let's see if we can't represent that with pictures. We could imagine that the idea of things canceling out is because numbers just mean quantity, and we can play with numbers the same way that we would play with sand in a sandbox. Here's what I mean. If I gave you a sandbox and I said it was level, we could say that that is going to represent 0. Nothing's happening on the sandbox, so that makes sense. And similarly, we could say that if I had a sandbox and it just had 1 hill in it, that would be 1. And perhaps I wanted to talk about what the negative of that hill would be, the opposite of having a hill. Well, we could call that just a hole. So we could say that I have a hole and that would be -1. And I could have piles that are X big. I could have piles that are 10 big. I could have 10 1 piles, however you want. We're just playing with moving sand in our sandbox. Well, let's see what happens when I start to talk about these piles that are a certain amount big and we represent them with these shapes. If I said, what is possibly represented by this picture? Let's see what we can find. So we're going to play around with, and I'll use blue. Let's try to identify each one of these. I have an X. I have a negative X squared. I have a negative X. I have an X. I have a negative 1. I have a 1. I have an X squared, and I have a negative X squared. So all in all, if I wanted to combine these, I would have an X, a negative X squared, a negative X, an X, a negative 1, a 1, a negative, or a positive X squared, and a negative X squared. And if you wanted to think about this even more fundamentally, remember that you can always think of all these things as just being added. So we could think of this as being adding my negative X squared and adding my negative X, and then I add an X, and then I add a negative 1, and then I add a 1, and I add an X squared, and I add a negative X squared. However you'd like is going to simplify out to the same idea, because now I have X, and then I have a negative X squared, and then I have a negative X, and I have an X, and then I have a negative 1, and I have a 1, and I have an X squared, and I have a negative X squared. Well, how can we simplify this? Imagine that these are all just piles in my sandbox. What could I combine together, right? And we'll draw that out. Imagine I have my sandbox, so that means I have an X pile, I have a negative, or I have an X squared hole, and then I have an X hole, and then I have an X pile, and then I have a 1 hole, and then I have a 1 pile, and I have an X squared pile and an X squared hole. Okay, we could even put in some labels here to keep everything nice and consistent. We're just playing around here. We're putting whatever we need in the picture. So this is my X, this is my negative X squared, this is my negative X, here is my X, here's my negative 1, here's my 1, here's my X squared, and here's my negative X squared. What happens when I try to combine all these together? Well, we can imagine that a lot of these piles are going to fill up a lot of these holes. So we have, for example, the X pile here is going to very much fill up the X hole, and we have the, let's see, a negative 1, we have a 1 hole. It's going to need our 1 pile to fill it up. I have an X squared pile, and I have a negative X squared hole. Those are going to simplify away. And so all in all, I think when we go through all of this, we'll be left with just a negative X squared and a negative, let's see, is that it? A negative X squared, and then we filled that one in. I think that's it, right? If we get confused, let's go back to our original picture. We have, let's see, this X cancels with our negative X squared cancels with our X. I have a negative 1 and a 1, and so I have an X left over. Okay, so I have a negative X squared, and then I have an X that was left over. So that's everything that's left over. That's my simplest version of my sandbox. Kind of fun that we can play around with pictures here and move things around. Okay, well now suppose that I wanted to make a rectangle, and then that I followed this rule. So any number you give me, we'll call it X. I'm going to add 2 to it, and then I'm going to make that be one side. I'll have subtracting 2 be the other side, and I'm curious about what would the shape be that I get from that. Well, similarly, I don't know what X is. I don't know what the numbers are, but I can represent it with a picture. So we'll do the exact same thing. Here's my rectangle. I'm trying to organize it out. On one side, I'm going to have my X, and then I'm going to try to take away 2. So I'll take away 2 unit blocks. And here I have X, and I'm going to try to add, we'll do 3 unit blocks. Okay, so I try adding 1 unit block here. I'll try adding another unit block here and a 3rd unit block here. Let's see what we can do for our picture. Well, X times X would be X squared. X times negative 1 would be my negative X. X times negative 1 gets me a negative X. And then I have X times 1 gets me an X, and then I have another X, and I have a 3rd X, and then over here I would have negative 6 of them, I believe, negative 6 units from negative 1 times 1. And so we could draw all these out, and then we could shade them appropriately so we don't confuse them. All of these are going to be our negative X's, and then I have 6 of these negative units. Now this might feel a little bit weird, but let me show you exactly what happens. Imagine that I said X was instead like the number 10. So what exactly have we accomplished here? Now if you give me X equals 10, I've created a rectangle where on one side I took 2 away from it, that gets me 8. And on the other side I put 3 on it, that gets me 13. And so if I figure out how big this is, it would be 8 times 13. That would be, let's see, 8 times 3 would be 24. And then 8 times 1 would be 8, so it would be 104 units. And that's actually represented right here. Let me show you how. X squared, and then what else do I have? I have plus 3x's, that's from the bottom left, and then I have a minus 2x, that's on the top right, and then I have minus 6. So I have in total over here, if x is 10, is I have a 10 square, I have 3 10 rectangles, I have the opposite of 2 10 rectangles, and I take away 6. So that's 100 plus 30 minus 20 minus 6, and I'll tell you what, that comes out to 104. Kind of fun. So what we've done here is we've really said that I have this expression which talks about a rectangle, and the rectangle is formed by adding 3 to one side and taking 2 away from the other. And I can always represent it in this way until somebody tells me what I'm starting with. And in such a way, it means that I've already pre-done all of my work. I've set up everything no matter what they tell me x could be. X could be 5,000, and I'm still just going to plug it in here. In fact, I could even simplify it one step more. Instead of x squared plus 3x minus 2x minus 6, we could simplify it to x squared and then recognize that 3 of these x's and taking away 2 of these x's is like having 3 piles and taking away 2 of them. So it's like having 1 pile left over. And at the very end, I have my negative 6 units. So this expression represents my rectangle, the size of the rectangle, no matter what. Kind of fun. Let's see how we can even play with this if we wanted to go in reverse. So now I claim I can make a rectangle with the tiles below. Can you? Let's see if we can do it together. We know this is an x squared. We know that we have 3 of these x blocks here, and we have the opposite of 2x blocks, or negative 1x, and another negative 1x gets me negative 2x. Then I have negative 6 of these unit blocks. Can we arrange these in a rectangle? Well, let's start with the biggest part first. We'll put the x squared in there. So we'll just start with the exact same way. Put the x squared here. And then let's imagine that I wanted to try to take care of these 3x's. So maybe I'll line those up as well. So now I have 3x blocks that I'll put right there. Okay. Where do I want to put the negative 2x blocks? I could put them down here, but I'm not really quite sure that they would arrange nicely. Let's see if we can mirror our original pattern. Let's put our negative 2x blocks right here. We'll shade them in so that we don't get them confused. And then I have my 6 opposite blocks, so I'll put that in right here. And then I'll want to make sure that all of the signs work out the same way that I know they should if I'm doing multiplication. So what would that be? This would be x units long, and then this would be 3 units long, so that'd be x and 3. And over here I would have what? X and one entirely negative row and another entirely negative row gets me the opposite of 2 positive rows for sure. So all in all, could I write this as x plus 3 times x plus a negative would be x minus 2? Well, for those of you who are paying attention, you'll recognize that these are the exact same blocks we were just playing with above. Take a look. Here I had x minus 2 that I started with, and I multiplied that by x plus 3. Is it true that this is the exact same thing as x minus 2 and x plus 3 being multiplied? Sure. This is what it means when I say that I'm allowed to commute. I'm allowed to switch the order of my multiplication, as it doesn't matter if I'm looking at 5 groups of 4 or 4 groups of 5. It doesn't matter. So here, again, we have this idea of saying maybe I'm going to start with some of these blocks and I can reform them into a rectangle. And what that means is that now I don't just have a pile. I have a pile of things that I can look at just the length, I can look at the width. And even more importantly, what it really says is that I can take something like x squared plus 3x minus 2x minus 6, and I could take something that is nothing but addition and subtraction of all of these different terms, and I can write them very simply using just multiplication. Kind of fun that we can take just a pile of objects and see whether or not we can turn them into a rectangle. Okay, so I'm going to leave this one for you. Could we make a rectangle that had the same value as the tiles shown here? And I'm going to give you a little bit of a hint. As it is right now, it's not going to work so much for being able to form it into a rectangle. You can start with having your x squared right here, and you probably want to be performing your blocks, your little opposite blocks, maybe do a 2 by 3 or a 3 by 2, but go ahead and put those in the opposite corner. But you're going to need to find a way to fill this up with x blocks and this up with x blocks so that it all balances out. You should recognize that there's going to be 2 that are needed over here and 3 that are going to be needed in this spot, but I only have 1 right now. How many more of these open boxes do we need to create? And if you create one more open box, remember that the only way to do that in our sandbox is to create a negative block that's the exact same way, so we maintain the value. So I'm giving you a little bit of a hint. I've created one and I've balanced it. How many more of these do you have to create so that you can organize this into the exact same rectangle shape that we had above? And then how would you represent that using your algebra? What does it mean on the paper if you're just trying to start with symbols? Because for example, I'm going to recognize that before I changed anything, I had an x squared, I had an x block, and I had 6 of these opposites. And after I created one of these open rectangles and created a negative rectangle or a shaded in rectangle, that was then I had 2 of these x blocks and I had a negative x blocks and a -6. Did I change the meaning? Is it the exact same? What else do I have to do? How much do I have to continue to grow these middle terms so that I can organize everything properly in a rectangle? That's an exercise for you. Okay, so now let's see if we can represent these as a picture. And after that, we'll have a pretty good idea of how it is that we're behaving with all these. So if I have this x times x plus 6 and this -5 of x plus 6, let's take a look at what that means. So picture-wise, that means I have x groups of x and 6. So here we go. We're going to start with x and 6, and I'm going to try to create x groups of them. So x groups of x is going to be my x squares, and then I have x groups of 6 is going to be 6 of my x's. Okay, so it's going to be 1x, 2x, 3x, 4x, 5x, and 6x. Great. On the other side now I have the opposite of 5 x blocks. So the opposite of 5 x blocks would be shaded in blocks. So opposite of 1, opposite of 2, opposite of 3, opposite of 4, and opposite of 5 x blocks would be 5 shaded in x blocks. Okay, so far so good. And then I'm looking for the opposite of 5 groups of 6. So opposite of 5 groups of 6, that would be the opposite of 5 times 6. That'd be the opposite of 30. So I'm looking for 30 of these shaded in blocks. 1, 2, 3, 4, 5, 6. And if you shade in 30 of them, so we'll go shade in another row, shade in another row, shade in another row, and then shade in another row. Again, we can see that we have a rectangle. We have a rectangle where we have x, and then -5, we have the opposite of 5 rows across here, and then we have x and 6 if we're looking at the columns. So here we are. Our rectangle is x minus 5 times x plus 6. And that's because here we really try to do factoring again. We recognize that common between both of these, I have an x plus 6. So in an x plus 6, if I can organize everything with a shared side, then I can factor that out and say, well, what remains? I have x plus 6 common between them, and I have x groups of that and the opposite of 5 groups of that. So this is where we get to understand some of the rules that we've been taught in algebra. You may have seen that we can, from this step, rewrite everything where we pull out the x plus 6, and then behind is going to be the x and the -5. And this is exactly why. It's because we have a shared side. So if we ever have a shared side, a shared term of anything, we're able to organize everything in that picture and then pull those concepts out. So let's take a look at this very last one. What do we have? We have, let's see, x, and then we have that we are adding 2, and then here we have x, and it looks like I have, I think this was a typo. I think these ones here, maybe not. I have a -1, but that's not a fully negative row. Oh, it would be if I switched these two. Okay, so we'll switch these two. We will switch those two, and then I have a -1 row, and I have a +1 row. And so all in all, I would have, let's see, x groups of x and 2. I would have a -1 group of x and 2, and I would have a +1 group of x and 2. And however you want to look at this, you could look at this as being an opposite that cancels out with this, or you could look at factoring everything out. You're going to get that I have x plus 2 common between everything, and then I have x minus 1 and plus 1. That really just gets me x plus 2 times x. Is that true? Is it true that I only have x plus 2 times x? Well, x plus 2 times x was this part of my picture, and everything else seems to cancel away, and it's because, again, I have piles and holes here that are filling each other in. So it's just playing with pictures and figuring out how do I want to take things away, move things in, factor things out. We're really just trying to say, what is the shape that I have? Can I look for a common side, and can I rearrange this in a way that has the same meaning, but possibly a different way of looking at it?